In this problem, a heavy beam of length 2L is supported by a roller on the left and a pin on the right. The configuration is symmetric, so that there are two overhangs, each of length A, and our task is to choose the length of the overhangs so that the maximum bending moment induced by the weight is minimized. We will solve this problem in two steps. First, we will assume that A is given and simply determine the maximum bending moment. Second, we will choose A so that the maximum bending moment is minimized. So we begin with drawing a free body diagram for the entire body. The horizontal reaction at the pin is equal to 0, and the total weight of the beam equal to 2W times L is equally distributed between the two vertical reactions. To find the internal forces, we need to make cuts. In this beam, we certainly need to make a cut on the left between the left tip and the roller. Then we need to make two more cuts, one in the middle of the beam and another is on the right side of the beam. Nevertheless, because the beam is symmetric, we can get away only with two cuts, one on the left and another in the middle. The cut on the right will give us the information that can be reconstructed from the cut on the left. Let me begin with the cut on the left. So that's a sign convention, and the free body diagram corresponding to this cut is shown here. Please compare this diagram with the sign convention diagram and convince yourselves that since the cut is on the right, we're looking on the right side of this diagram. The equilibrium equations involve some of the forces on Y and some of the moments about the cut point, which I denote by capital X, and the equations can be solved to give us the expressions for V and M. Next, let me proceed with the cut in the middle. Again, the sign convention and the corresponding free body diagram is shown here. Again, let me emphasize that the cut always at a location X, so that the length of the left segment here is A and the length of the right segment is X minus A. The equilibrium equations follow from this free body diagram, and let's walk slowly through the last equation because it's perhaps the most complicated one. So the force WL generates a negative moment because it is clockwise about the cut point, and the arm of this force is X minus A. The distributed load has the resultant W times X. This resultant produces a positive counterclockwise moment. Because the distribution is uniform, the resultant has to be placed in the middle, and therefore we have the arm for this force equal to X over 2. Finally, we have the bending moment M of X. The solution to this equation is given here, and so now what we have that the bending moment is given in the following form. So between 0 and A, M of X is given by this expression following from the cut on the left, and between A and L, the cut. The second cut gives us the expression here. We can plot these functions, and you can see that if I plot the function in the middle and extend it beyond L, there is symmetry here. And this symmetry implies that I can take the left branch of the function and have a mirror image of it on the right. At any rate, this function doesn't have any critical points, either between 0 and A or between A and L, and therefore the only points that I need to check are the endpoints. On the left, I have 0, then I have to compare the value at the roller, minus WA squared over 2, versus the value in the middle of the beam. Let me add that whether this function's enter as, or this value enter as positive or negative, it's somewhat immaterial because I'm interested in the absolute value of the bending moment. And therefore, what I need to compare are the value of, at this point, absolute value of this and absolute value of this, and find the minimum between two of them. Now, the way I will think about this minimization is the following. Let us suppose that one of these values is larger than another. Then I can adjust the value of A to bring the larger value down and the smaller value up. And this process will continue until two of them are equal to each other. And therefore, the optimality condition is that these two values are equal, or if I remove the absolute value, I have the WA squared over 2 is equal to plus minus the expression in parentheses. So there are two possibilities. First involves the plus sign, and the corresponding equation is given here, and we can solve for A, and A is equal to square root of 2 minus 1L, or approximately 0.41L. Another option is to take the minus sign, and then this will give me the expression A equal to L. It is clear that if A is equal to L, it means the roller and the pin converge in the middle of the beam, and the beam becomes a seesaw, and certainly this solution is unacceptable for us. Therefore, the only acceptable solution is the one associated with the positive branch, where I is approximately 0.41 L. The corresponding value of the bending moment could be computed by substituting this value either into this expression or this one, and at the end we get the expression that the maximum bending moment is equal to less than 10% of WL squared. Now, let me complete this problem by comparing two designs. One is optimal, as identified by us, and another design involves just simply supported beam, 2L, and the supports are at the ends. And so for this case, we just calculated the value of the maximum bending moment, and it is equal to 0.086 WL squared. This second problem can be analyzed if we go back and evaluate M max at A equal to 0. And this will correspond to the value of half WL squared. Alternatively, it's easy to solve this problem by itself. just from scratch. So upon comparing the two answers, we find that the ratio of the bending moments, the non-optimal case versus optimal case, is larger than a factor of 5. Therefore, the optimal design increases the effective strength of the beam by a factor of 5. Thank you.